In the last video, we discussed what a homeomorphism was exactly, and we constructed a homeomorphism between the Cantor set and an infinite subset product of the set 0, 1. Now, we're going to look more into it. The Cantor set homeomorphism may have felt a little bit contrived, so instead, it would make sense to think about something that might come up a bit more naturally. Being the astute student that you are, after learning about homeomorphisms, you start to think about what other topological spaces have homeomorphisms between each other. One of the spaces that we've been working with a lot is the real number line and the open intervals that it provides. Well, let's look at the open interval from -4 to 6. Is there anything special about this compared to, say, the open interval from -6 to 4? They both have the same lengths, and they're both just lines on a number line. What about how they compare to -2 to 3? Now, they no longer have the same lengths. Can we find a homeomorphism between these? A homeomorphism between -4 to 6 and -6 to 4 comes somewhat easily, since we can just shift everything to the left by 2. Similarly, going from -4 to 6 and -2 to 3, you could just divide each value by 1/2, and this also yields a homeomorphism. If you are unconvinced, I encourage you to try proving that they are homeomorphisms using the definitions from the previous video. Okay, so we've now found these homeomorphisms from -4 to 6. What about a general line like A to B? What is that homeomorphic to? We can extend our previous homeomorphisms to show that it is homeomorphic to A minus x to B minus x, as long as the length is conserved and as long as the values are still within our bounds. We can also take any multiple of these values. But what if instead we see if we can show that it is homeomorphic to 0, 1? This comes a little bit less naturally, or at least it shouldn't be as natural as some other homeomorphisms, but at the same time, this one isn't too difficult either. We can use a bit of deductive reasoning to figure out what our homomorphism might be. We know that f of a should be equivalent to 0, and f of b should be equal to 1. This is because f of a should be our minimal value, and f of b should be our maximal value, since a and b are our minimal value and maximal value respectively. This should give us the idea that there should be some like f of x equals x minus a term, since f of a would give us 0, but then trying f of b now yields b minus a. This isn't necessarily 1. It could be 1 if b equals a, but then we get kind of a trivial open interval. But what if we instead try to force it to be 1? We can force it to be 1 just by dividing b minus a. This now gives us the function f of x equals the quantity x minus a divided by the quantity b minus a. Now, do these work for the quantities f of a and f of b? It seems like it. What about another value that should have an obvious mapping, like f of a plus b over 2? This is the middle point of our interval, and what we should expect is that we should get 1/2. And as we notice, our function does give us 1/2. At this point, this mapping should feel like it works, but we still aren't completely sure about it. This problem is, however, especially easy because we can easily construct an inverse. Since f of x equals x minus a over b minus a, we can invert it by creating the function f inverse of x equals x times the quantity b minus a plus a. Plugging these in, we see that we do indeed get 1 as an output, which means that it is invertible. We explained last time that if a function is invertible, it follows that it is homeomorphic since f of x is continuous as well. Now, as an exercise to the reader, can you show that the closed interval from a to b is homeomorphic to the closed interval from 0 to 1? What about the open interval a to b to c to d? Are they all homeomorphic? I hope you enjoyed the video.